Hey guys, and welcome back to this class, Artificial Intelligence, Reinforcement Learning in Python. In this lecture, we are finally ready to start formally discussing value functions. We saw value functions earlier when we discussed tic-tac-toe, but that was informal and only for the purpose of gaining intuition. So if you see any discrepancies between how we defined the value function before and how we're defining it now, you should consider everything we do from here onward to be more correct. The value function, given a policy and a state S, is equal to the expected value of the return, given that you are currently in state S. Note that because of how it's defined, the value function is dependent on the policy. This is because any future state transitions depend on what your policy is. Also notice that the value function depends only on future rewards. That means the value of any terminal state is 0, because by definition, you won't be doing any more state transitions and hence you won't be receiving any future rewards. Let's now do some algebra. Notice that the return is recursive. We can separate r of t plus 1 and r of t plus 2, and so on. Because this is the expected value over pi, that means we can express pi as a probability distribution. In particular, we can express it as the probability of doing an action A, given that we're in state S. Since expected values are linear operators, we can do the two terms in the expected value separately. So let's first consider just the expected value of r of t plus 1 given S. Because everything is stochastic, this is governed by two probability distributions. First, there's the policy, pi of A given S, that determines what action we'll do. Once we have the state action pair S and A, there's also the probability distribution, P of S prime and R given S and A, which we can marginalize to get P of R given S and A. So both of these probability distributions are needed to find the expected value. And of course, we can write this in terms of the full joint state distribution probability as well, by summing over S prime. In fact, we can use this to calculate the expected value of anything, given the policy and the current state. Therefore, we can also use this to calculate the second part of the expected value we saw earlier. Take a minute to stare at this or pause the video until it soaks in. Now I say that somewhat jokingly, as I know that for a lot of you, telling you to simply stare at this won't help you because you have no idea what you're looking at. However, I know that some of you are going to take that literally, so let me just clarify. I don't literally want you to stare at the screen without actually using your brain. So what I really actually want you to do is write this down. I know this probably sounds crazy, given that we are in the age of computers, but I promise you that if you get a pen and paper and you write down this derivation, it's going to make a lot more sense than just staring at it on the screen. I know that most of you are proactive and you do this on your own, but this is for those people that just don't think of stuff like that. So to break this down, how do we go from line 1 to line 2? Well, this is just replacing the expected value symbol with the relevant probabilities. Remember that this is just the definition of expected value, which we covered just a minute ago. However, I've done something a little tricky here, which was to add a nested expected value for the second term, which is just to the right of gamma. So I took away one expected value, but then I added another one. Now why did I do that? Again, we have to go back to the rules of probability. First, you recall that the expected value of an expected value is just the same expected value. You can do this infinitely, and it won't change the answer. So you can say the expected value of the expected value of the expected value, and so on. Therefore, if I have one expected value, let's say e of a plus b, I can insert another expected value in there, let's say e of a plus e of b, without breaking any rules of probability. Second, we make use of the conditional expectation rule. This is also called the law of total expectation, in case you want to look it up on Wikipedia. If you've never seen this before, don't worry too much. It looks a little strange, but it's actually pretty easy to prove on paper. I strongly recommend doing so if you've never done it before. It'll help you understand this derivation a lot better. What we've done is sort of use the law of total expectation in reverse. We know that any conditional expectation could go in this spot, but we use this specific form because we know that it corresponds to the value function for s prime. And of course, this easily brings us to the third line, which is just replacing what we know is the definition for v of s prime with v of s prime itself. And so now we can appreciate this equation in all its glory. We see this recursive structure. V at some state just depends on V at the next state. Even though what we care about is the total future reward, which by the way could be infinite, we don't have to look that far into the future. And by the way, just so we're clear, it would be impossible to count up to infinity. We know that V of s prime already encapsulates the future by definition, so V of s prime is as far as we need to look. In other words, in order to tell the future, all I need is to just look one step ahead, just one. If I'm playing a game of tic-tac-toe or I'm playing chess, what does this tell me? If I want to know what to do next, I just look at what is the reward I get by going there, and what is the value of the state I arrive in when I go there, or what is the reward I get when I go here, and what is the value of the state I arrive in when I go here. And if I'm an intelligent and rational agent, I'll pick the state with the maximum value. But now we're getting ahead of ourselves. This has to do with how to find an optimal policy, which we'll cover in a future lecture. So that's why this equation is so important. In any situation, we want to do a global optimization. We're not so much interested in making $5 in the next minute. We want to know how to make $1 billion in a lifetime. But reinforcement learning says you don't need to consider every future step. As long as you know the value function, then you can always safely look just one step ahead. Not two, not three, not infinity, just one. Everything I need to know about future rewards is already encapsulated in the value function by definition. This recursive equation has a special place in reinforcement learning, and it's the equation from which all the algorithms we learn are based. It's called the Bellman equation, named after the famous mathematician Richard Bellman. Bellman pioneered the technique known as dynamic programming, which you may have learned about in your algorithms class. It's related to recursion, but it's efficient since it builds up the solution using a bottom-up approach. In fact, one of the techniques we'll learn about for solving MDPs is called dynamic programming. There is one more value function we'll need to learn about in our discussion of value functions. What we just learned about, v of s, is called the state value function. There is another value function, q of s and a, called the action value function. It's called this because the action a is also a parameter of the function. Notice that because q has two inputs, the amount of space we need to store it is quadratic. In particular, the amount of space we need is the size of the set of states times the size of the set of actions. In later sections of the course, you'll see that the value function we use depends on what algorithm we're using. There are some algorithms that specifically apply to only the state value function or only the action value function.